So for this exercise, we're going to look at how to calculate the voltage, or what we'll call the electric potential difference, in a defined E field. And I did feel like I should start with a picture of a little bit of snow in the Cornus cusa tree outside my house. That's not a lot of snow, but it's enough snow to do this exercise from home instead of the classroom. So a couple quick reminders, things that you already know that we'll use today. First, you know that you can calculate an electric field, E, as kq over d squared. That's the equation we've been using to find the strength of an electric field if you know the charge and how far away you are from it. And remember that the electric field strength is measured in newtons of force per coulomb that would feel it. So it's a force per coulomb of charge. We also know once you've found an electric field, the force that a charge would experience is simply the E field strength times the charge that shows up at that point to feel it, or F is E times Q. And then the third equation that we reach back for comes from the idea of doing work, which is when a force gets applied over a distance. So the three equations we'll think about are E is kq over d squared, F is EQ, and work is FD. But today, to calculate the electric potential difference, we're really just going to use these two. F is EQ and work is FD. We'll assume the E field has already been determined for us, and we'll see what that looks like. So this is the slide that shows us the electric field. And you can see that what I have here are two charge plates. On the left side, I have a positive plate. On the right side, I have a negative plate. And between them, you can see the electric field is being indicated by the lines that connect the positive to the negative. And the reason they go that way is that we remember that we would use an imaginary positive charge to determine the direction of the field. So you can see at point A there's a positive charge, it says plus Q, and that if I put that charge into this field, it would feel a force that would be directly to the right, being repelled away from the positive and being attracted over towards the negative. So the direction of the field is from A to B. Now let's think about that in terms of potential energy. And I like this slide because on the top it shows the potential energy changes in the electric field, and at the bottom it shows a mass on a hill and makes the analogy to the potential energy changes in a gravitational field. So you can see in the top, you can see that if the charge was released at point A, it would fall to the right over to point B. And that falling, it would fall this way to the right. That falling isn't really falling like gravity, it's falling in a charge field, where it's being pulled to the right, and the force of the electric force that's attracting it to the negative plate. So the potential energy is higher at A, and it loses potential energy as it falls over to B. Just like in the hill on the bottom, the mass has a higher PE when it's up on the hill, and as it rolls down, the PE is converted into kinetic energy, and it has a lower PE when it reaches the bottom of the hill, and it gets down to the bottom. We could even say it has 0 PE if it couldn't go any lower. So our next step is to remember that the force that a charge would feel if I put it into the field is E times Q. Or here, in this slide, they're telling us that force equals Q times E. That's the same thing, E times Q or Q times E. So this charge is in an electric field, and we could even define the strength of it. We could say, imagine that the field is 150 newtons per coulomb of force per charge, and this charge at point A would feel a force equal to Q, the amount of charge, times E. So if it was a 1 coulomb positive charge, it would feel a force of 150 newtons. And within this field, the field strength is the same everywhere. So it would feel a force of 150 newtons at point A, and it would also feel a force of 150 newtons at point B. Now notice that if I let go of A, it would fall down to point B, and it would lose potential energy in doing that. That is, it would spontaneously be repelled downwards in a change of potential energy of its position as it left the positive plate and was attracted towards the negative plate. And you can see there's a 0 down here at the bottom, which is showing you that the potential energy would reach 0 if we allowed it to fall all the way down to the negative plate. Now, that's going to happen spontaneously. That is to say, it will lose energy falling down, but on the right side, over here, we can see a situation where we're going to try to take that positive charge at point A and we're going to drag it upwards to point B. And if I want to do that, I have to apply a force equal to the EQ, force that's felt in the field, and I have to apply that force over a distance however far apart A and B are. So now I'm doing work. Now I'm taking this charge at A and I'm lifting it against the force that's pulling it downwards, and in lifting it up to bring it up to B, I have to do work. And the work I have to do is equal to F times D. And that work represents the change in potential energy, delta PE or delta U. To get from A to B, I must do work to raise its potential energy and put it in the higher place in this field. Okay, so now let's get to the actual calculation. Here you can see the same kind of diagram that we've been looking at, but in this case, the field isn't oriented up and down, it's oriented horizontally from right to left. And the first thing to see is that I'm actually defining the field strength here, that the electric field strength is given to us. Let's move it to the pen instead of the grab. The electric field strength is given to us. It's 150 newtons per coulomb. So a 1 coulomb charge would feel a force of 150 newtons anywhere in that field. You can see 2 points defined, point B and point A. And the first thing I could ask you is, at which point does a positive charge have higher potential energy? And if you think about it for a minute, you should be able to know that the higher potential energy would be at point B, right? That's higher potential energy because if I let go of it at B, it would fall to A. If I let go of it at A, it would fall farther to the left, and I have to do work if I want to lift it from A to B. So we're going to actually make the calculation here and see what it takes to find out what the difference in potential energy is between point B and point A. And that defines what we call electric potential difference, or our voltage. So when we look at our two equations, F is EQ and work is FD, we can pick any charge we want. So let's imagine a 1 coulomb charge. Let's imagine a 1 coulomb charge at point B. Let's imagine a 1 coulomb charge at point B moving from B to A. If it moves from B to A, it's going to lose potential energy. If it moves from A to B, I have to do work and give it more potential energy. So let's talk about doing the work to drag a charge from point A to point B. Well, work is force times distance. What's the force that it feels? 150 newtons. If it feels 150 newtons of force, over what distance do I actually have to make that force apply? I have to apply that force over a distance from A to B, which is defined here as 0.003 meters. So 150 newtons times 0.003 meters is going to give me the work I have to do and the potential energy difference between point A and point B. So now we can finish the calculation and we can say, first of all, work equals F times D. So I'm going to imagine that I have a force of 150 newtons, and that's because it's a 150 newton per coulomb field, and I'm going to multiply that times 0.003 meters, the distance that I have to travel from A to B. A to B. If I do that, you can see actually I'm going to get something that you can actually do. 3 times 150 is 450. I'm going to go 1, 2, 3. So I'm going to get 0.45 joules. 0.45 joules is actually the amount of work that I have to do to drag the charge. Now a volt is defined as 1 joule of potential energy change per coulomb of charge. So 1 joule per coulomb is 1 volt. So what we see here is that we've defined the potential energy change by making our calculation as 0.5 joules for a 1 coulomb charge. That means in our story, if a positive charge was dragged from A across to B, it would have to have a potential energy increase of 0.45 joules per coulomb. In other words, from A to B, the electric potential difference is actually going to be 0.45 joules per coulomb, or 0.45 volts. So we need to think about positive and negative for a minute. 0.45 volts because it's actually 0.45 joules per coulomb, but is it positive or negative? Well, what it said on our earlier slide is that if a positive charge loses potential energy, that's positive voltage. If a positive charge gains potential energy, that's negative voltage. In this case, going from A to B, I'm doing work. I'm actually dragging it, quote, uphill. And so that means that a positive charge is gaining potential energy, so that means in this case it's negative. So I'm going to say in my case, A to B, it's going to be a negative voltage minus 0.45 volts between A and B. So voltage has a directional component. We have to know the electric potential difference from A to B is the opposite sign of the voltage from B to A. So that's our calculation for volts. We'll give you some more practice with this, and you'll get a chance to make those calculations on a joules of energy per coulomb charge basis.